How does the concept of time change near a black hole? Music. How did Einstein describe a distinction between past, present, and future? These are some of the questions that we will explore in this video as we embark on a journey through the mysterious and mind-bending world of black holes and the concept of time. Join us as we dive into the incredible power and strangeness of these cosmic behemoths and discover the implications of traveling to a black hole, from the extreme physical effects on the body to the fundamental changes in our understanding of space, time, and gravity. In principle, if you stay outside the event horizon of a black hole, right? If the black hole is a mass m, then there's a beautiful little formula that you can work out for how big the black hole is. You take 2, multiply it by Newton's constant g, multiply by the mass of the black hole, and divide by c superscript 2. That number tells you how close you can safely get to a black hole without being pulled in. If you stay outside that number, 2gm/c superscript 2, then, in principle, you can go to the black hole's edge, turn around, and come back. And if you do that, when you return, you'll note that you've come back to the future. If you spend time near the edge of a black hole, time elapses there more slowly. So clocks back on Earth will be ticking fast, while your clock ticks slowly. If you spend a year hanging out near the edge of a black hole, and then return to Earth, it might be 10 years, 1,000 years, or even 1 billion years into the future. So, the journey that you think is through space, Earth to black hole and back, is actually also a journey through time. Because when you come back, the amount of time that will have elapsed on Earth is far more than you expect. Einstein's theory of relativity revolutionized our understanding of space and time. According to this theory, time is not absolute and universal. Instead, it's relative and depends on the observer's motion and gravitational field. The passage of time is described as a 4th dimension, along with the 3 dimensions of space. However, the concept of time having a direction is still a topic of debate among physicists. Some believe that time moves only in one direction, from the past to the future, known as the arrow of time. Others suggest that time is symmetric, and the arrow of time arises from the initial conditions of the universe. Einstein's relativity gives us a very different way of thinking about time, in which we imagine that every moment is as real as every other moment. It's not just that the present is real, the past is gone, and the future is yet to be. Rather, every moment, past, present, future, is equally real. This is what gave rise to Einstein's own poetic description, where he said, "The distinction between past, present, and future is only an illusion, however persistent. We are so familiar with the fact that physical happenings always unfold in one temporal direction. There's an intuitive sense that time has a direction, the so-called arrow of time. The classic examples are, if you drop an egg, it splatters. It never unsplatters. If someone dives off a diving board, they enter the water, but you never see someone jump out of the water, untumble, and land back on the diving board. That's an important observation, because when you see reverse-run films, they appear ludicrous, conflicting with your intuition about the nature of time. But here's the amazing fact. When you look at the laws of physics, as currently formulated, all of them, when properly interpreted, treat the future and the past symmetrically. They are on equal footing. This means that any sequence of events allowed in one direction is also allowed in reverse. There's even an algorithm. If you have any physical process and want to reverse it, all you need to do is reverse the motions of the particles involved. The implications of time's relativity become particularly striking near black holes. As you approach a black hole, the gravitational force becomes stronger and stronger, causing time to slow down. If you are able to survive these extreme conditions, you could potentially experience some of the most extreme phenomena in the universe. Thus, understanding the nature of time is crucial to understanding black holes and the effects they have on their surroundings. If this concept feels abstract, we can visualize it with a space-time diagram. Picture time on the vertical axis. You set off a beam of light that spreads out into a cone, a light cone. The geometry of space-time is so distorted near a black hole that beyond the event horizon, the direction of time and space twists such that light cannot escape. That's why the black hole is black. No light can escape it. The idea of traveling to a black hole and returning is popular in science fiction, but it's not merely fictional. It's theoretically possible. However, the extreme gravitational forces would have serious physical effects on your body. The difference in gravitational pull between your head and feet could stretch your body, a phenomenon known as spaghettification. Imagine you're near a waterfall, paddling your kayak. If you can paddle faster than the water's flow, you can escape, but if you can't, you're doomed to fall. Similarly, space itself falls into a black hole like a waterfall, and the speed at which space falls is the speed of light. Since nothing can go faster than light, you can't escape once you cross the event horizon. So, near a black hole, you're doomed. You might as well paddle toward it and enjoy the ride down the throat of the black hole. That's another way of thinking about it. At the edge of a black hole, space is falling over the edge at the speed of light. Since nothing can exceed this speed, escape is impossible once you're in. The implications of traveling to a black hole are not just physical. If you were to survive, you'd witness phenomena that challenge everything we know. Time is not universal. It depends on your motion and gravitational field. If you go near a black hole, where gravity is much stronger, the time warp can cause major differences between clocks at different distances. Popular culture has used the scientific concept. Interstellar, for example, depicts astronauts going near a black hole because of gravitational time dilation. What feels like a few hours to them equals 23 years on the mothership. Kip Thorne, the science advisor for film, ensured scientific accuracy. Of course, this is all theoretical for now. But the fact that it's possible to contemplate such journeys is a testament to the power and mystery of black holes. Despite their strangeness, black holes continue to fascinate and inspire scientists and the public alike. While traveling to a black hole may still be science fiction, advances in our understanding of black holes and time are paving the way for new discoveries.